Hello, welcome to lecture 4 on kinetics, and today we'll be answering a question on using the initial rates to determine the order of a reaction and the rate law overall. So, starting off, the question states, given the initial rate data, determine the rate law and rate constant for the following reaction. This reaction, we have bromate reacting with bromide and proton to make bromine and water. So, looking at our checklist as we compiled in other videos, we have 4 steps. These first 3 steps we're going to have to repeat for each reactant, and then at the end, once we have all this necessary data, we can go on to determine the rate constant. So first things first, let's determine the experiments we'll be referring to for this particular reactant, bromate. So, the conditions for finding a right experiment are that we have to look for experiments where the concentration of our desired reactant is changed, whereas the other concentrations of our other reactants remain the same. So, looking at this table here, we see that experiment 1, all our concentrations are the same, whereas in experiment 2, bromate that we're looking at in this part of the question is increased, whereas the other concentrations have stayed the same. So we can use these 2 experiments, 1 and 2, as our reference for the increasing or changing rate. So secondly, once we have found the experiments we're going to be referring to, we want to then find the ratio, or say the factor by which these numbers are increasing. So we know it's quite obvious that for the concentration of bromate is increased by a factor of times 2, because 0.1 times 2 is 0.2. And then, more importantly, for the rate, we need to see how the rate has changed. So we see that in experiment 2, the rate was 1.6 times 10 to the minus 3 moles per second. Whereas in the first reaction, it was 8 times 10 to the minus 4. If we do this division, we find that the increase, the factor of increase, is a nice round number 2. And now that we have both these numbers, we can go on to making our expression, the third step of our checklist. So we know that the amount of reactants is going to have an effect on the rate by some inordinate amount, where we call it x. So very simply, as we've seen that the increase here was a factor of 2, and that the increase of the rate is also a factor of 2, we put it like this, where the x is a power of this number here. If you rearrange, you find that x is simply equal to 1. X equals to 1 in this case is telling us that with respect to bromate, the reaction is first order. And now that we've done this for bromate, we can then go on to do it for bromide. So, step 1, finding the experiment we'll be using for reference. So here, as you see, we need to find bromine, where bromine is varied, and the other reactants are held at the same concentration. And looking at the board, we see that, for example, experiment 2 and experiment 3 are rather similar, where bromine is the only one that's varied. So we'll be using these 2 experiments as our reference. Now that we've found our reference, we're going to then go on to finding the factor or the relative ratio as to what these quantities have been increased by. So again, quite obvious for our increase in reactant, it's a factor of times 2. So we'll leave this on the side here to remind ourselves that the reactant has changed by a factor of times 2. More importantly, the rate, looking at this part of the rate, if we write it down as the fraction to the power of 3, and then if we look at this and we actually complete the fraction, we come out with the number 2 again. And like in the other example for the bromate, we just combine these 2 in step 3, combining these 2 to make our little expression in order to deduce our order. So again, we're left with 2 to the power of, let's say, y this time, equal to, again, 2. Same piece of algebra, we're left with this equaling to 1, and therefore overall being first order. And finally, we're going to do this for the H plus or the proton. Now looking at our H plus here, again following the rules from our checklist, we have to find an experiment where H plus is being varied and the other concentrations are held the same. So looking at the table, upon quick analysis, we see that this is experiment 1 and experiment 4. Our second step, in finding our ratio, again, repeating the same steps as we did with previously, we'll see that the reactant has increased by a surprise, factor of 2. However, looking at the initial rate, there's a much bigger difference than factor of 2. So let's just simply go work this out. We have 3.2 times 10 to the minus 3 over 8 times 10 to the negative 4. This comes out to be a factor of actually, in fact, 4. So when we come together to make our expression, making this say z this time, for clarity's sake, equals to 4, when we solve algebraically to find z is going to come out to equal 2. And this, unlike before, where our other reactants have been first order, this tells us that H plus in this reaction is second order. Now that we found the order of the reaction per reactant, we're now going to find the rate constant using a bit of maths and a bit of algebra. So here we go. We know that when we find the rate is given to us in an equation like so, where you'll have, using our example, say this reactant here, and another reactant, and another one. All of these to the power of the number that we just algebraically found out, or in other words, the order of the reaction. So now, with this expression written out like so, we can then go on to fill in the information that we know. So the first step when we're wanting to make the rate law, or the rate constant, sorry, is that we want to go on to using an example of an experiment itself. So for the sake of simplicity, I'm going to take experiment 1 because we have some nice low numbers here. So the rate in this equation is going to be 8 times 10 to the minus 4. And we want to fill in the information that we've already found before to find K. So K times concentration of bromate to the power of the order that we found previously. And now it's common shorthand that if the order is 1, you don't have to write 1. But for the sake of clarity, I'm going to show you now. But just know that if you do see an expression without any numbers on the brackets, you can assume it's a first order. So for the rest, I'll do this. And for the proton, we found it was second order, so make sure that you write a power of 2 there. Okay. Now that we have this written out, we can then go on to actually multiply these numbers and come out to find that all of this will equal 0.0001. And now we can divide this by that to give us our K, and in this case our K equals a nice easy number, 8, and the units for which will be moles to the minus 3 per second. Now the units for this can be easily found out by just doing some simple algebra and putting in our units per bracket and continuing the algebra as normal. So exactly what you do to the numbers, you just do to the units to find your overall units for your constant. Now that we've completed that example, I'm now going to show you another example of a reaction, and I want you to do it yourself. So in this reaction we have permanganate with chloride and protons reacting to form manganese, chloride, and water. With the initial rate data we found experimentally. Now it's over to you. Pause the video now and try it yourself. Okay, I'm going to show you how to do it now. So starting off with permanganate, we'll go through our checklist and we'll complete the question. So permanganate, let's select an experiment where permanganate concentration has been changed but the other reactants have been held. So looking at the table, we can see that this is experiments 1 and experiments 2. So that's our first step, experiments 1 and 2. The second step in our checklist, finding the ratio, finding the factor in which these amounts have increased, we can thus go on to writing our rates and our concentrations for our reactant. Okay, this ratio here determines how much our rate has increased. This has been an increase, is calculated to be 6.23. Over here, for the reactant side, for the permanganate, the increase is of 0.25 divided by 0.1 is 2.5. And step 3, making our expression. So our value here, 2.5, the factor in which we increased our reactants, raised to the power of, let's say, x for this question, equal to 6.23, which was the factor at which our rate has increased. Now, solving this algebraically, we find that x, now it's going to be a decimal number, of course, but we can approximate this to the nearest full number, and in this case it's 2. So as we said before, x equals 2, x equals 1, this denotes the order of the reaction. So here we have a second order for permanganate. Okay, now that we've completed it for permanganate, we're going to go on to do it for the chloride. So chloride, let's choose our experiment. Experiments 1 and 3. In this case, step 2, finding the ratio. So our ratios will be 1.6 times 10 to the minus 2 over 5.2 times 10 to the minus 3 for our rate. And for our reactants, we'll have 0.3 over 0.1. And now, looking at here, we'll make the same division process. We'll find that this equals 3.1. Here, this is easy maths, I hope I can do this. 0.3. Not even. 3. And now, armed with our numbers, we can make our expression. 3 to the power of, in this case, we'll say y, equal to 3.1. With a little bit of approximation, we can say that this is equal to 1, telling us that this reaction is first order. And finally, for our hydrogen ion, we'll decide the reactions we're going to use. We'll say for hydrogen, where the concentration is held, but the others, this will be reaction 1 and 4. And now, second step, finding the ratio of the rate change and the ratio change for the reactant. Okay, now we have these ratios, we'll find them out. So this is 1.42, and this, I'll get it right this time, is 2. Now making our expression. Two to the power of, say, z this time, equals 1.42. And now, this is an odd exception, because normally when we rearrange this to find our power here, we have a full number. But in this case, if you've noticed, and we rearrange this, and we want to get an approximate answer, this will come out to be about a half. So what does this mean? Well, in this case, we can just say we have a half order reaction. Half order with respect to H+. Last step, and finally, we can determine the rate constant. So as you already know, when you write out a rate equation, you know that the rate here is equal to a constant K times the concentrations of our reactants. So for this question here, we have permanganate here, we have the chlorides here, and we have H+ here. And now, as we had done previously, we determined the orders of given the reactant, the order given that reactant. So, with the order of manganate here being 2, we'll insert a 2 here. So raising the number we're going to put in there, we're raising it to the power of 2. As you remember for chloride, we found that to be order 1. I'll put it in there anyway. And then the H+ was the odd exception when we had a half power. So there's not to worry about, you can simply just put it in there, and as you'll see, the equation will work itself out either way. So, the first step is to take an equation from the experiment. So, experiment 1 I'll use. We have 5.2 times 10 to the minus 3 moles per second as our rate. Put in our K, and the concentrations we'll be using are 0.1 for everything, so I can just write that down now. And now, using a little bit of algebra and a little bit of mathematical magic, we can get to here, where we'll find K. We rearranged it, 16.4. Now, for the units for this, like last time, it's quite simple. You simply put in the units into where you're going to be performing your mathematical actions. So here, we'll put moles, moles, and moles. And when you rearrange, you find that they'll cancel out, and you'll get an overall unit of minus 2.5 per second. I hope you enjoyed watching this video, and I hope you learned something. Join us again next time. Goodbye.